As mentioned earlier, Python comes with an extensive standard library, an aspect of Python often referred to as batteries included. The standard library is structured as modules, a topic we'll discuss in depth later in the course. What's important at this stage is to know that you gain access to standard library modules using the import keyword. The basic form of importing a module is simply the import keyword followed by a space and the name of the module. For example, let's see how we can use the standard library's math module to compute square roots. At the triple arrow prompt we type import math. Since import is a statement which doesn't return a value, Python doesn't print anything if the import succeeds, and we're immediately returned to the prompt. We can access the contents of the imported module by using the name of the module, followed by a dot, followed by the name of the attribute in the module that you need. Like many object-oriented languages, the dot operator is used to drill down into object structures. Being expert Pythonistas, we have inside knowledge that the math module contains a function called square root. Let's try to use it. But how can we find out what other functions are available in the math module? The REPL has a special function, help, which can retrieve any embedded documentation from objects for which it has been provided, such as standard library modules. To get help, type simply help. We'll leave you to explore the first form, for interactive help, in your own time. We'll go for the second option and pass the math module as the object for which we want help. You can use the spacebar to page through the help, and if you're on Mac or Linux, use the arrow keys to scroll up and down. Browsing through the functions, we can see there's a math function for computing factorials. Press Q to exit the help browser and return us to the Python REPL. Practice using help to request specific help on the factorial function. Press Q to return to the REPL. Let's use the factorial function, which accepts an integer and returns an integer. Notice how we need to qualify the function name with the module namespace. This is generally good practice, as it makes it abundantly clear where the function is coming from. That said, it can result in code that is excessively verbose. Let's use factorials to compute how many ways there are to draw 3 fruit from a set of 5 fruit using some math we learned in school. This simple expression is quite verbose with all those references to the math module. The Python import statement has an alternative form that allows us to bring a specific function from a module into the current namespace. This is a good improvement, but it's still a little long-winded for such a simple expression. A third form of the import statement allows us to rename the imported function. This can be useful for reasons of readability or to avoid a namespace clash. Useful as it is, we recommend that this feature be used infrequently and judiciously. Remember that when we used factorial alone, it returned an integer, but our more complex expression for combinations is returning a floating point number. This is because we've used Python's floating point division operator, the single /. We can improve our expression, since we know it only ever returns integral results, by using Python's integer division operator, which is a double /. What's notable is that many other programming languages would fail on the above expression for even moderate values of n. In most programming languages, regular garden variety signed integers can only store values less than 2 to the power 31. However, factorials grow so fast that the largest factorial you can fit into a 32-bit signed integer is 12 factorial, since 13 factorial is too large. In most widely used programming languages, you would need more complex code or more sophisticated mathematics merely to compute how many ways there are to draw 3 fruits from a set of 13 fruits. Python encounters no such problems and can compute with arbitrarily large integers limited only by the memory in your computer. Let's try the larger problem of computing how many different pairs of fruit we can pick from 100 different fruits, assuming we can lay our hands on so many fruit. Just to emphasize how large the size of the first term of that expression is, calculate 100 factorial on its own. It's a number vastly larger even than the number of atoms in the known universe, with an awful lot of digits. If, like me, you're curious to know exactly how many digits, we can convert our integer to a text string and count the number of characters in it, like this. Let's move on and look at integers, strings, and other built-in types in more detail.